Hi, welcome to Shash Code. My name is Lisa Shashkova, I'm a software developer, and today I would like to present the second part of the series on my channel, Design Patterns in Python. And today I would like to discuss structural design patterns, the second group in design patterns. I already have a presentation about the first group, creational design patterns. You can watch it now if you missed it for some reasons. And today we are going to discuss structural design patterns. Creational design patterns were created to simplify the way how objects are created, and structural design patterns describe the structure between classes and objects. And today I'm going to show my examples in Python programming language, but the coolest thing about design patterns is that they don't actually depend on programming language, so you can use any object-oriented language you want or you know and apply the same knowledge about solving some architecture tasks apply this knowledge to your real life tasks. I'm just using Python because it's really cool and it's really to read Python code even if you don't know Python. You can easily understand it. Okay, so today we are going to have 7 structural design patterns, and the first one is adapter. Adapter allows classes with incompatible interfaces work together. You know, it might happen pretty often when you use some library class, so you call some method, and you can't access it, you can't change it, it's some third-party code, and you have another implementation which has changed and which wanna call some another functionality. And you have to this subjects and you need to make them work together. In this case, adapter design pattern will help you. Let's look into some example. For example, we have some library class which has some library method which is called by client code, and we want to call, for example, real class instead with some real method. Yeah, and what can we do here? We can define another adapter class which is inherited both from library class and real class, and look what we do here. We override library method and we call the real method inside it. So what happens here? Library class doesn't know anything about real class. Real class doesn't know anything about library class. But with the help of this helper class, our adapter, we can make these methods, these classes work together. Now, when we have a client code which takes a parameter library class, again, it doesn't know anything about real class. It knows only about library class and it thinks that it calls some method from library. But in reality, we can pass here not library class, but our adapter, because it's inherited again from the library class. And what will happen here? Let's try to run this code and see what happens. What happens? First, when we called client code with instance of library class, it just called library method, and we can see library method called in the output, which is pretty predictable. But when we passed adapter, instance of our adapter class, you can see client code doesn't know anything about it. It just called library method. But in reality, it called method from our adapter, and in fact, it called real method from our real class. And that is really cool because we had two classes with incompatible interfaces, and now we made them work together, which is actually pretty cool, right? So you can use this adapter design button whenever you need the following functionality. Okay, let's move to the second structural design button, and it's called Bridge. Bridge design button allows us to decouple an abstraction and from its implementation, so they can change independently. The easiest way is to look into some example. Again, nothing new here. For example, you're creating some image editor. Well, pretty common example, but it's really easy to explain it. So in this image editor, you can draw different shapes. Here is a shape class. Of course, there might be some circles or squares or many different shapes. And also you can draw them with some color. In our class, so we have a class color, which has method draw circle with the following parameters. And we have two inheritors, red color and blue color. And for the shape, we need to store, we have class shape and its inheritor, for example, class circle with exact implementation. And the bridge here is this link. So we store a link in a shape class to an instance of color. And now we know with which color we want to draw our shape. And here, when we create some circle implementation of this interface, we know all the necessary parameters, and we can call this method of the color class, just because we store link to an instance of color class. And again, our client code doesn't know anything about this complicated thing. It just takes a shape parameter and just calls draw method of this class. But in reality, we can pass different parameters here. So let's just call it. Let's just call our method. We call bridge and see what's going on here. So we created a circle with the link to the red color. We created a circle to the with the link to the blue color, and we called our client code. We just calls draw method. And here we drew red circle and we drew blue circle. Why is it cool? Why is this design pattern actually needed? The coolest thing is that now we can change to these classes independently, shape and color. We can, for example, add some functionality or some implementations, and our client code wouldn't need, there is no need to change some interfaces, create some common interfaces for implementation. Now they can be changed independently. For example, we can change another method here, draw, and there is no need to change color class for that. Or we can add some implementation or another method to our color class, and again we store a link inside our shape class, and link is enough. There is no need to modify our shape class for every change in our color class. So the bridge class here is shape because it stores link to another interface, to the color class interface. And that's really cool. That's why you can use it. And that's actually, I've met this pattern pretty often in my programming experience, in my programming life, and I would say it's pretty popular. Now let's move to the third structural design pattern, and it's called Composite. Composite is a structural design pattern which lets you to work with composite and simple objects the same way. So in other words, for example, you have all your objects you are working with can be separated into two classes: simple, it's some object, or composite, which might contains links to several or simple objects or composite objects. In other words, your model can be represented as a tree. You know, like a tree as a data structure when you have nodes and edges. And each node might have children, maybe 0 children. In this case, it will be a leaf, or several children. In this case, it will be composite object, so-called. And you might see the following structure in real-world programs. And composite design pattern allows us, gives us a way to work with such structures. For example, well, it's actually not a very natural example, but it's better than nothing. For example, we have class box where we have some items. So you can add items, remove items, check if it's composite or not. So we can, for example, we can store a link to a parent of our box. And the box class has two implementations. Simple box, as you remember, a leaf in our node which doesn't have children, which contains just some item in it, or composite box, which might contain some other boxes inside it. In other words, it's a tree, and for example, you want to implement some simple function. For example, here's we're writing the list of all the items of all the structure inside our box structure. For example, I don't know, you want item has some cost and you want to traverse all the items in your system and count the sum of summary of all these items. And composite pattern allows you to work with these nodes the same way. So visit, for example, visit all the nodes in your structure and work with them the same way. As you can see, it's a tree, an object from the graph theory, and of course we can visit it. Most likely you have seen my video about traversing nodes in a tree. It's what's the difference between breadth first search and depth first search. If you missed it, you can find it right here and go and watch it right here. And actually I've already discussed it with you, my friends. So I think this topic will be pretty easy for you. Our operation, visiting all the nodes, will look like this. So we check some this operation, and this is method where we visit all the nodes in our tree. So for simple box, it doesn't have children, so we just return some item it has inside it. And for composite box, it's the following. So we first call the same thing for all our children, and after that store results in a list and return results for all our children. If you watched the video about breadth first search and depth first search, I think you can easily understand which algorithm is implemented here. Is it BFS or DFS? I'm waiting for your answers. Write in the comments of this video. I will be happy to see that you watched my previous video and understand this topic pretty good. Okay, so now our client code just takes some instance of box and calls this operation. Again, the coolest thing is that client code doesn't know anything about simple box, a composite box. It just doesn't care. The coolest thing is that it just calls operation and gets a result. And the implementation is hidden, and you work with to these classes the same way. Let's build our tree. So we created composite box. We created the left box, so-called, with 2 children, simple box. We created the box number 2. You can imagine the right child with 1 simple box inside it. And we added this 2 boxes to the root of our tree. Now we can just simply call, let's just run our code, and we did something wrong. Well, because I think here we just need to call operation and not, well, sometimes it happens. I edited it right before here. Yeah, so what can we see here? That's exactly what we showing here. So we have a tree with a box inside it. The first box has 2 children and the second box has just one child. And it just prints elements inside our tree right to the output. And so that means that it works, and that's really great. Yeah. So you might face the following structure in your real life code, and now you can see that all these algorithms like BFS or DFS, which might look a bit unnatural when you learn them, but in fact you can face them in real world programming tasks. Cool. Let's move to the 4th structural design pattern, and the 4th design pattern is Decorator. If you're using Python for your daily work, you might know that it has decorators, and actually it's very, if you know what it is in Python, and design pattern is actually pretty similar. So decorator pattern dynamically adds and overrides behavior of some existing method or object. That's exactly what Python decorators do. Like it takes some function and changes its behavior, calls inside it, or do some additional stuff, do some stuff before real function call or after call, or do some different things. For example, let's consider a more object-oriented example. Like you have class notification, which sends some notification to the user. It has implementation, for example, warning. So send warning to user of our service. Now we can create decorator, which takes a notification as parameter, but it has also method. The interesting thing, it inherits from the notification class, and it also has a notification method send, which calls method send of our instance of notification. But we can create different implementations of this decorator. For example, email decorator or SMS decorator. We can send notification via email, or we can send notification via SMS, and many other things. So if notification is some library function and we can't change it, but we need to add implementation to it, we can use decorator for it. And we can, for example, for email, we can do some preparations and then call real library function. Again, our client code doesn't know anything about decorators. It just takes notification object and calls send for it. But in reality, and when we do it for the first time, that works exactly like this. If we create default notification, nothing will be broken, but we can create email decorator, so fake notification, so pass it to the same client code, and it will show email notification, which is actually pretty cool. Or additionally, we can create SMS decorator and pass the first decorator to it. So we can create a composition of decorators, and it will combine all the necessary decorators, decorator for decorator, and so on and so forth. Let's try to run this method right now. What's going on here? So yeah, look, for the first piece of code, it just called warning. For the second, for email decorator, it called just send warning through email. And in the third case, it sent 2 warnings for email and for SMS, which is actually pretty cool. Why is it cool? Because client code doesn't know anything about our implementations, but we created this class and now we can use it inside our code, and there is no need to change a library code with notification class or client code which uses it. We just created some secret object and passed it to the correct places inside our code. That's actually pretty cool. Cool, that was the fourth button, decorator, and now we are moving to the fifth. The fifth design button is a facade. Facade design button which provides a simplified interface for some complicated things. It's exactly like in real life. There is facade, which is beautiful, and nice things, but behind it, a lot of terrible things might be hidden. The same might happen in software development, which happens pretty often. Like you can see only beautiful picture or some things for the client, but inside it can create terrible, complicated things, systems, and a lot of other stuff. For example, I don't know, you have some complicated subsystems. We have some class subsystem 1 which does some operations, subsystem 2 which does another set of complicated operations, and in reality you don't want to show it to your client, to the user. You just want to skip all this initialization steps or some preparation stages. You just want to give one beautiful method which user can call and do all the necessary things. I don't know, you're working in some video game and you need to establish, I don't know, the map of your game, add some characters, define a lot of stuff, initialize scores, and do things like that. And Facade design partner will help you here because it's just a class or a method which has one or several easy to understand simple methods which you can call and which will hide all these complicated things right inside it. So from the client point of view, it just takes Facade and calls this operation, and that's it. And inside it, some terrible things happen right here. Additionally, you can send, of course, some parameters to Facade. It can either create it inside it, or you can pass these subsystems as parameters. Let's execute this code again. What happened here? Yeah, so you can see we just called inside client code, we just created Facade and called this operation, but in reality it called a lot of complicated things, but we don't even care about it. So if you want to hide some complicated logic, you just can use this design pattern, but you should be very careful here, because there is high probability that you will create a so-called God object inside your code, because that will be, facade is just one point which calls different like classes, yeah, and different programming points. They all come to this class, and it might happen that it will become, well, one big object which stores too much information about the whole application, programming states, different links to different objects, and once when you want to decouple this, your program, into different subsystems or parts, it will be difficult, because one day you might realize that too much code depends on this one type, one instance of facade, and that's not really good for architecture. So you should use this design pattern really carefully. Great. Now let's move to the sixth design pattern called Flyweight. Flyweight, a design pattern which reduces the cost of creating and manipulating a large number of similar objects. This situation also might happen pretty often when you have a lot of objects in your program, but you realize that big parts of these objects are actually duplicated. It's just the same objects, they store a lot of repeated information, but you need to, all this information is the same, but it's all stored in memory, because you created just separate objects. So your program creates a store them in different parts of memory in your program, which is not actually good, and it's not a rational memory usage. You can do it the better way if you know that there are a lot of objects in your program, for example, like video game, right? And you have cars in your video game. It's like, I don't know, a city, big city map, and there are a lot of cars. And of course, cars in general, they are pretty similar. There are several models, there are several colors, and actually there is no need for each car object store information about its model, about its color, about everything. You can store it just once and store information inside your object to this information about car and type, model, and after that it will be really easy for you to save a lot of RAM inside your program. For example, let's look into this example. So, for example, we have a car Flyweight here. Here we pass some shared state, list of strings, but it also has a unique state, some additional items which can't be shared. So each object has some common things and some unique things. And we pass these unique things to the operation and call it. And we have a separate class, for example, car factory, which does the following. First of all, of course, it can take initial flyweights as a parameter, but in reality, what happens here? When you try to get flyweight for some state, it can generate a key, a unique key, and it stores information about flyweight, where key, and the exact flyweight objects. And it can, the most important part is actually here. So you're trying for each new object, it calculates the key, checks if we already have flyweight object for this key. If it exists, it just reuses the same object, and otherwise reuse the same object, and otherwise, if we don't have such flyweight, it just creates new object. And after that, there is a method for showing all the flyweights. So how it works? For example, we created our car factory, for example, Chevrolet pink, Mercedes red, and BMW white. Cool. We can show this flyweight. And now we want to add another car to our big city map. We want to create a white BMW for user with name James. What happened here in this add car to map method? First of all, we trying to get flyweight for our brand and color. Our factory returns it for us, and we do operation with some parameter which isn't included into our flyweight. So in our case, it's owner. Let's see how it works. I think it will be even better for understanding. Okay, so first we created car factory with 3 cars, model color. We can see them here. And now we want to add BMW white. We already have a flyweight for BMW and white. So what's going on here? We are reusing flyweight here. We called the exact operation for our BMW and for user James, and we still have the same 3 flyweights because we reused existing. Now when we call Mercedes, which is silver Mercedes, what happens here? Again, we are checking, going to our flyweight factory, but now we need to create a new one because we didn't have silver Mercedes before. We add it, we call this operation, and now we have 4 flyweights in it. That's actually how it works. And I want to add again some Python specific example here because you might know when you work with some programming language, you create pretty often some standard objects like strings or numbers, and most likely you create a lot of them in your program, some primitive objects. And different programming languages, for example Python, also try to optimize memory for inside your program. For example, I don't know, number 1. You can use it many times in your program. You can use it as index or +1 or -1, or really use it a lot of time. And there is no need, it's the same number 1. There is no need to create, I don't know, 1,000 of objects with the same value. And Python optimizes this thing, and it doesn't create object for each thing. It just creates the same object and shares links to the same object when you use it in your program. For example, here, look, we created 2 variables, A and B, with the same value, and compared their identifiers. Identifiers are the same, so it's the same object. And otherwise, for example, dictionaries, we created 2 the same dictionaries, 2 different variables, but their identifiers are different because they're different objects. You might, for example, one day you might want to update this collection and remove some element from this collection, so it's not rational to share the same object. You just need, it's much easier to create 2 different objects. But with numbers or, for example, strings or some other popular primitive things, Python language uses the same objects. Also, something similar happens in Unix operating systems when you fork processes. So when you create new child process, you might expect that operating system copies all the resources, all the memory to the new child process, because it's a separate process now. It has a separate memory, separate everything. But in reality, it doesn't exactly copy copy all the necessary resources. It fakes copy, so it will duplicate some, I don't know, a piece of memory only when you try to edit it, only when you try to change it. Before it will be the two links to the same memory address. And only when you change something, Unix system will create a copy and override value there. That's why you can create a lot of processes pretty fast and without any problems, and that's how operating systems also can save resources during process creation. So actually you can you can face the same technique in real world examples. Great. Now let's move to the next and to the last, I hope, design pattern called Proxy. Proxy design pattern provides a placeholder for another object to control access, reduce cost, and reduce complexity. In other words, you have some object, but you need to add some additional level of access for it. For example, you can check if you have access, or you want to control it, or you do some additional thing. Actually, it's pretty similar to Decorator, but it's different. Again, for example, we have some class which has method database request, so it sends request to some database, and well, it has implementation which does this, sends this request. And we want, for example, we want to check if user caller of this method really have this access to this database. What can we do here? We can take a link to this real subject and override this database request method and add some additional functionality to it. So here we not just directly request database, we firstly check if we have access to this database in reality. And again, client code, it doesn't know anything about our proxy object, it just thinks that it has subject, instance of subject as parameter, and just calls method and doesn't know anything about it. But in reality, when we call this client code, we replaced subject object with our proxy object, and now we added this additional check for it. Let's see how it works. Yeah, so when we called just with subject, it just called, requested some database without any additional checks. But now when we created our proxy object, we now can check, do we really have access to database? Aren't we going to add some bad things inside it? No, everything is fine, so we can call it right inside our code. Actually, that was the last structural design pattern which I would like to discuss with you today. I said about it in the first part of my design patterns videos, but I want to repeat it again, that why design patterns are cool. They're cool because actually there are a lot of very similar and repeated tasks in software development, especially in software architecture. When you think about structure of your program, different classes, how they different connections between these classes, objects creation, or additional functionality which you want to add to this, the whole systems. And actually many of these tasks were already solved by other people before you, and instead of reinventing the same ideas again and again for each new generation of software developers, it's much simpler and it's much easier to learn all these existing patterns, all these existing solutions, and you can apply them to your code base and focus on some other functionality, on some additional features in your program, or some maybe additional patterns, parts of your design which aren't covered by this existing well-known famous design patterns. So it will make your work much more productive, and which will make you to become a better developer. At least I hope so. So it doesn't depend, design patterns, they don't depend on exact programming language. It's just the main idea for object-oriented languages, and you can use them as soon as you recognize the situation in your code. So the best way to learn them is, of course, to write code in complicated big systems and read code. This is also very important, because sometimes you might don't even know, but you most likely you've seen many of these patterns in different code bases, but you might didn't notice that it was this design pattern or that design pattern or combination of these design patterns. But that's how it works in reality. I do hope my videos will be helpful for you and will help you to recognize design patterns in existing code base and apply them in the places which are where you write new code. Thank you very much for watching me today. I hope you liked the video. Subscribe to the channel so you won't skip the third part of design patterns. There's still another group of design patterns, behavioral patterns, and I think there will be even more patterns there, and they will be even more interesting than creational and structural design patterns. So thank you very much for joining me today, and see you in the next video. Bye.